Okay, so to give a bit of context to my talk, we've recently seen that people have become more and more interested in supplementing their null hypothesis tests with more careful estimation of the magnitude of the effects as well as its uncertainty. And in general, we've also seen a trend of people become interested in Bayesian methods, Bayesian statistics. So my talk will be kind of at the intersection of these developments. So my aim here is to introduce this analysis approach and build an intuition for how it works, why it might be useful. And, well, it won't be a mathematically rigorous treatment. I also like to acknowledge that the main analysis that I'm presenting today is taken from this excellent tutorial paper by Sorensen and colleagues. Okay, so let's keep it practical and start with the data. So we recently got a coffee machine in the common room here at the CBU. So I thought, okay, that's kind of an interesting question. How does that influence the amount of time that people spend in the common room for the break? Of course, we also need to take into account if there's cake, yes or no. And then on the surface of it, you have an experiment, right? You have two factors, coffee and cake, each with two levels. We'll assume that the outcome variable is normally distributed, and I've measured 25 people from the CBU in each condition. Let's just say that's true, okay? So the data looks a little bit like this then. So clearly, having the coffee machine there makes people spend more time in the common room. There also seems to be an effect of cake, but perhaps it's a bit more diminished when the coffee machine is available. So maybe an interaction effect, right? We can do an ANOVA. And in this case, we see that, unfortunately, there's a p-value of 0.06 for the interaction. So then we can't reject the null hypothesis for the interaction effect, which is a bit disappointing. Okay, so that's a pretty straightforward analysis. So what's the problem? Well, first of all, the null hypothesis itself isn't really that interesting, actually. It's a bit like a straw man that you can refute as long as you collect enough data to cancel out the noise variance. Formally, the p-value tells you, given the null hypothesis, what's the probability of observing a summary statistic that's as extreme or more extreme than what you've actually observed. So that maybe is not as intuitive as you think, because you would think we keep the data as what's fixed and we try to see what the probability of my hypothesis is. But that's not what we're doing here. More generally, in my opinion, when you do null hypothesis tests, you're basically condensing your data down into a yes or no answer. And it's not really helpful for cumulative science. And also, I don't personally think it's reasonable for any one study to give a kind of yes or no answer to a big research question. Also, another problem is that p-values don't really speak to probability in the way you might think they do, at least when we talk about the null hypothesis. So for example, if you just give me a p-value of 0.80, you might intuitively think, oh, well then there's a really big chance that the null hypothesis is true, right? But if the null hypothesis is true, so if there's truly no effect whatsoever, then the distribution of p-values is uniform. So under the null hypothesis, all p-values are equally likely. That's also a bit counterintuitive. And there are more commonly appreciated issues like multiple comparisons and optional stopping. Okay, so then what do we want? Well, what would be really great is if we could say, given the data that I've collected, what's the probability of my hypothesis? And this is something that Bayesian statistics deliver. I've illustrated Bayesian inference here in the context of simple linear regression. So we're just looking at one parameter here, the slope. We start with some prior information. So we say that the slope is centered on 0 with some variance, so this is a normal distribution. Then you collect the data. In a frequentist regression, you assume that there is a single best line of fit, and you recover the best estimate of that, which maximizes the likelihood. But here we talk more in terms of distributions, where some values are more plausible than others. And, well, the posterior distribution of our parameter, the slope in this case, is drawn slightly in the direction of the prior, because the posterior is proportional to the likelihood distribution and the prior distribution. This is just a toy example for one parameter, but usually you have many, many parameters, and then these distributions become quite difficult to work with. So then there isn't really an analytical solution to this problem. But what we can do is we can characterize or approximate the posterior distribution using a sampling technique called Markov chain Monte Carlo. So what is MCMC? Let me break it down for you. First, the Monte Carlo bit. So this refers to the law of large numbers. We're stuck here with a situation where we have a distribution. We want to know what the distribution is like, but we don't know the true values of the distribution, the true parameter values. But the law of large numbers says that if you are able to randomly draw samples from this distribution, you end up with a collection of samples, this one, this histogram here at the top, which will converge to the true expected value. So this characterizes the posterior distribution very nicely. Okay, so how do we draw samples from the distribution? That's the Markov chain bit. So the best analogy I've come across is where you think of this as a kind of treasure hunt. So you've got, your friends have hidden a treasure somewhere, and they'll tell you if you're getting warmer or colder, right? So you walk step by step, and each step you evaluate your progress based on the feedback from your friends, and then over time you will converge to the location of the treasure. That's the idea. And it's basically this is a really simple algorithm, which is quite similar actually to that idea. So you have some initial estimate. You propose a new value, which could be just adding some random noise to that initial estimate. And then you need to determine if you should accept this proposal, yes or no. To do this, you look at your distribution of estimates. So if the new value makes that distribution, gives it a greater density, it means you're basically getting warmer. This ratio will be bigger than 1, and you accept this new proposal and you move on. If, however, the proposed value makes your distribution less dense, then some of the time you reject it and some of the time you accept it. The reason you don't just flat out reject all of those is that you don't want to get stuck too soon on one single value, and you want to really travel a range of plausible parameter estimates. This is called Markov chain because when you propose a new value, that proposal only depends on the current estimate. So it doesn't take into account all of the history in your chain, and that's the Markov property. Okay, so typically you would reiterate this for something like 2,000 samples, and you have a number of separate chains. Okay, so now that we have an intuition for how that works, let's talk about the actual model that we're going to fit. So to return to our data, we want to know what's the effect of coffee and cake and their interaction on break time. And we also want to take into account individual differences here. So that's a linear mixed model. This is just your outcome variable, so a vector of observations. That's a design matrix. So this basically codes for the levels of the factor. And this beta vector is what we're really interested in. So this is really what we want to estimate here, the posterior distributions for these parameters. These here are the adjustments by subjects, so you allow the parameters to vary between individuals, and as always you have some residuals. Okay, and in R you can quite quickly actually kind of set up a list of components that refer to this linear mixed model that I just showed you. So you don't have to worry about the exact code here, but I'm just saying that you can set this up quite quickly. And how do we actually fit the model? We use a bit of software called Stan. And Stan is, well, it's a programming language in its own right. So in principle, it has nothing to do with R. But what we do here is we run this Stan model via R using an interface package called rstan. Okay, so I mentioned Stan is a language in its own right. So it may be a bit intimidating when you see this code. At least I was intimidated. But basically, I recommend that you check out this paper that I mentioned at the start, because they really do an excellent job at breaking down this code line by line and kind of building an intuition for how it works. Okay, so we'll take this code, save it as a .stan file, And from there, it's actually quite simple. So you've got this command in R. This is the bit of stand code. That's a list of objects that refer to the linear mixed model that we want to fit. In this case, I want 4,000 samples per chain and 4 chains. Okay, and then you run that, you wait for a couple of minutes, and then what we should end up with is a collection of samples for each of our parameters of interest. So first we need to inspect how our sampler behaved, and to do that we make these trace plots. So you can think of the x-axis here as time, so this is the number of the sample, the iteration basically, and on the y-axis is the parameter value. And what you're looking for is a fuzzy kind of caterpillar, and I think that's a good description for this plot here. These are some examples of when it goes wrong, right? So here you can intuitively see that it doesn't look like the sampler is really converged on a value, so it's still trying to search the real estimate basically. Okay, but now I'm just going to move forward with the samples that I have here. I'm basically going to squish those plots into separate histograms, and then you end up with this. So this is kind of the key result of this analysis, okay? Now, you can think of these distributions here. So each of these distributions contain plausible values for our parameters. And you can think of the mean as the magnitude of the effect, and the spread of the distribution as your uncertainty about the effect. I'm going to focus on the interaction here because that was kind of the controversial one with a p-value of 0.06. So the mean here is, well, it's minus 0.19. So it's not 0, but it's quite close to 0, right? So it doesn't seem like there's a very big effect. Also, the 95% highest density interval of this distribution overlaps with 0 just barely. So maybe then that makes you say that there isn't really an interaction effect of interest. But you might say now, well, it's still a bit dichotomous now because you're just looking at 0, so it's still kind of black and white thinking. And one additional thing we can do is we can say a priori we have a certain region of practical equivalence. So perhaps if there was already a lot of research on the CBU coffee machine, then I would have set this up properly. But anyway, let's just say for now that this is what we would say a null effect. We can see quite clearly that there is very strong overlap of this interaction distribution with the region of practical equivalence. Okay. Now, of course, inevitably, when you do all of that analysis, all the effort, you get a comment like this. So I'll try to give you a take-home message here. Basically, what I like about this analysis, it tells us the probability of our parameter estimate, our hypothesis, given the data. We're able to incorporate prior information, which can be practically very useful if you have complex models that fail to converge otherwise. And I hope you agree that the plot I just showed you quite intuitively gives you an idea of the magnitude of the effect and its uncertainty. Now, I've given you a very harsh, kind of one-sided view here. There are some downsides. So if your data is very noisy or biased in some way, then your estimates will be noisy or biased as well. So it's not really straightforward to control for that. One thing you can do is, which is what we've done here, if you set up your model hierarchically, then if you have one really oddly behaving subject, it wouldn't really have much of an influence on the fixed effects because of shrinkage towards the mean. And also, this isn't a conventional analysis. So if you want to report this in a paper, I imagine you would have to spend a lot of time in the methods and the results section kind of explaining what you've done. So yeah, that's a practical consideration. Okay, well, if you want to kind of reproduce the analysis and figures, I've put this repository online, so check that out if you're interested. And thank you for your attention.